This is a short video for some of the exercises in the special sequences lecture, lecture 3, and this is the first video in the sequence. This one will be on monotonic sequences. I've put the definition in this OneNote that I've exported to a PDF, and you can look at it on Canvas along with the video. You can mark it up. I've put solutions to a number of problems down. So let's just kind of go ahead and get into this. We're trying to make this kind of very efficient in going through these problems. So, this definition just defines an increasing sequence in terms of, the every subsequent term is at least as big as the one that preceded it, or a decreasing sequence, in which case each term is, no larger than the term that preceded it. So that's basically it. That's an increasing and decreasing sequence, and we call either one if it monotonic sequence. And there's some trivial types of monotonic sequences like constant sequences or monotonic sequences. The main result we have at our disposal, and in fact it's quite useful in proving the Bolzano-Weierstrass theorem, is that all bounded and monotone sequences must converge. And the way the proof works, and I've included it here just so that you can see it in the text, or if you don't want to open the textbook, you can read it in these notes. The proof starts by showing that if you have a bounded increasing sequence, then it must converge to the supremum of the set that's defined by that sequence, the set of numbers defined by that sequence. And they just go through and say exactly this is the totality of the proof. It's a paragraph, it's not that long, and you should really read it carefully. You're basically asked to redo that result in exercise 10.2. That's part of the individual homework that's due this Friday. And you're doing it for a bounded decreasing sequence. So this just here so that you can see the context of everything as well, but you see that, soups play a big role. All right. So anyways, besides having to apply that result, which, just real quickly means we have to show a sequence not just bound or not just monotone, but also bounded, right? So there's two hypotheses, two parts of the hypothesis of this theorem that we really have to verify, that a sequence is bounded and monotone, and then we'll have that it converges. Although this theorem does not tell us what it converges to. It's just that a bounded monotone sequence converges. So there is some limit. So you could say, great. How do we actually show that a sequence is monotonic? Well, you just use the definition like anything else. If you want to prove that a sequence is decreasing so that you want to verify this condition, well, then what you actually work with is this difference, Sn minus Sn plus 1, and you just show that that's in fact greater than or equal to 0. And similarly, if you want to show a sequence is increasing, then you show the difference in the opposite direction, that the difference of the n plus 1 term minus Sn is actually greater than or equal to 0. And that's what you do. Now, this may involve induction. In fact, it may involve a fair bit of induction. And I'm actually going to go through a little bit of example 2 that's in the text, but I'm going to present it in a more top-down approach. And I'm actually going to show you kind of all the inductive arguments that take place. So it's the same content that's in the text, but it's presented differently. So it might be of use to just, go through it in these notes, maybe listen to me talk about it, maybe not. So anyways, we have the sequences defined recursively. Usually that means we're probably going to have to use induction to prove the things we want to prove about the properties of the sequence. And we have that the first term in the sequence in 5 and all the terms thereafter are defined by this formula. You take the square of the term of the previous term, add 5 to it, and then divide by 2 times this previous term. And then they compute, a couple terms, the second and third term from that recursive formula. And then there's this statement, hey, note a simple induction argument shows that all the terms are greater than 0. And I say, well, if it's so simple, why don't you do it? And so, in fact, well, we have shown it for the first 3. You really only need to show it for 1 to establish the inductive hypothesis that you will then assume it's true for the first n cases, meaning that you're assuming that the nth term up to the nth term is greater than 0. All the terms up to the nth term is greater than 0. And then you just look at the final part of applying the inductive hypothesis here, which is, well, the n plus 1th term is defined in terms of, this term that's greater than 0 and all these other things that are greater than 0. And so it's greater than 0. So yeah, it's a simple inductive argument, but let's go ahead and write it out. So then we want to go apply theorem to 10.2. So we want to show it's decreasing. Now, it says all this other stuff, but you might kind of ignore that for now and just say, like, how would you even determine any of this stuff? Well, let's just see how this shows up in an inductive argument that actually requires yet another inductive argument. So you say, well, the first thing I want to show maybe is that the sequence is decreasing. So we say, well, look, I've computed, well, I'm given the first term and I use the recursive formula, I compute the next two, and I get a sense that, yeah, it is decreasing. So I'm going to assume that this holds for the first n cases because I've established the base case that induction requires, and then I make the inductive hypothesis. All these terms are now, less than the term that preceded them. So then you work with this difference, and we want to show Sn minus Sn plus 1 is greater than or equal to 0 to imply that Sn is greater than or equal to Sn plus 1. That's what it means to be decreasing. So you can't write this down because that's what you're trying to prove. You need to start with this difference and establish that it's greater than or equal to 0. So I start with the difference here, okay? And then I just work it out. There's a little bit of algebra, finding a common denominator. And then I come to this term, and I say, well, I've established by this previous inductive argument up here that the Sn terms are non-negative. So I know I'm not dividing by a negative number. In fact, they're positive, so I know I'm dividing by a positive number. So the only way that this can be greater than or equal to 0, and I really only need to establish greater than or equal, is if this numerator is greater than or equal. So it's like, okay, I need that. Well, how could I prove that? By induction. So the first term is 5. Well, that's greater than the square root of 5, which is what you need in order to establish this argument that we're trying to get to above, or the conclusion we're trying to get to above. So, okay, we've established the base case for yet another inductive argument. Assume the first n terms in this sequence are also greater than the square root of 5. How do you show that the n plus 1th term is greater than or equal to the square root of 5? Well, you take the n plus 1th term minus the square root of 5, and you establish that that is greater than or equal to 0. That's what you do. In fact, we do it strictly here. This is a strict inequality, greater than 0. So, this is what I start with. I start with the difference, and my goal is to show that it's greater than 0. Same thing, find a common denominator, and then I end up doing just a little bit of algebra and factoring everything. Lost a parenthesis along the way. Get that back. Excuse me. Here we go. My markup. Okay. And because we've established that the Sn terms are greater than 0, that was from our first inductive argument in the whole thing, we have that term is greater than 0. And then we have terms that are strictly greater than square root of 5. So this term is greater than 0, and we're squaring it. So it's definitely greater than 0. Certainly not negative. So that's it. That's what we needed to show. So we've had 3 inductive arguments in order to get that this result holds, that it's a decreasing sequence. And then because it's a decreasing sequence, the first term bounds it above. Part of our inductive argument actually showed that it was also bounded below. And so the whole sequence is bounded. So we have it's decreasing and bounded. Theorem 10.2 applies. The sequence converges. We don't know what it converges to, but we can actually figure this out. We've done this with recursive sequences back in section 9. So you just pass to the limit everywhere, because Sn converges to S. That also means that Sn minus 1 has to converge to S. And then you use limit theorems, and then some algebra, and then you make some, reasoning about why maybe if of all the possible limits, there's maybe only one that can actually work because of some bounds that we have. So that's what's going on in a nutshell in this example. It's a good example because it shows how one inductive argument kind of begets another inductive argument. And all in all, it's a bit involved, but it's not as if it's not straightforward. The inductive arguments kind of reveal themselves as you go through the work of trying to prove the sequence is decreasing or increasing based on your computation of the first few terms. So the other things I've shown in here, I just a few. I'm showing part F in these notes. You don't need any induction here because it's a very explicit sequence, so you can just do things directly. The one thing I do show in this, by the way, is actually how you can say what the limit is. We know it's 0 from calculus, but if we don't have L'Hopital's rule, how would you show that this actually converged to 0? And I actually show you how to do that using kind of like rewriting this sequence by raising it to the power 1 over n, and then raising that to the power n, and then using other results. So, okay, and then kind of a typical generalization of the squeeze theorem, which would just be that eventually a sequence is between 2 other sequences that converge to the same number. That would be the obvious generalization. So that's something you should go through a little bit more carefully on your own. And then I also include the solution to 10.9, which we did in class. And again, inductive argument here. And that's it. So I'm going to stop this here to keep it short, but read through these carefully. It's good review. It's good practice to go through these problems on your own, but now you have a guide, and hopefully listening to this was somewhat useful.